Welcome, nocturnal minds, aboard. Your learning journey starts now. So, picking up from our last discussion on identifying and dismantling pseudoscience, we naturally arrive at the very heart of how science actually works: representation. Most folks, maybe even some of us, initially think of science as just a bunch of words, equations, and articles. You know, the stuff you write down. But hold on, is that really the whole story? Think about it. Can language just float free? Does saying red magically make something red? No. We need eyes, we need context, we need tools. Science, being scrupulously applied common sense as Huxley put it, should be no different. It doesn't just use language, it builds upon these fundamental, nonverbal ways we interact with and understand the world. And when we look at the history of science, this reliance on non-linguistic tools is crystal clear. Think back to ancient Greece. Geometry wasn't just abstract symbols, it was about drawing things out with a compass and straight edge. Fast forward through centuries of maps, diagrams, charts, all ways of showing, not just telling. And today, forget about it. We're drowning in visualizations, simulations, data graphics powered by computers. These aren't just pretty pictures, they're essential windows into reality. Imagine trying to grasp the output of a complex climate model or a protein folding simulation just by looking at a spreadsheet of numbers or a wall of code. You'd go insane. These tools give us access, epistemic access to things our raw senses or simple language could never handle. They bridge the gap between raw data and understanding. Now, let's talk math. Galileo famously declared nature's book is written in the language of mathematics. Sounds definitive, right? But is math just another language? Hold that thought. Consider representing a pendulum swing with x equals a sine omega t. Does that equation itself capture the swinging motion? Not directly. It represents a mathematical function, a set of ordered pairs. Only when we interpret those pairs as time and angle values does it start to represent the physical motion. So, the representation chain is formula represents function. Function represents motion under specific interpretation. The success hinges on how well that function mirrors the motion in the aspects we care about. It's not quite like saying the cat is on the mat. This idea generalizes beautifully. An abstract model, often mathematical, represents a real-world phenomenon by highlighting some shared structure or form. Think of using a simple geometric shape to model a molecule, or a differential equation to model population growth. Language helps us point to the model and say, hey, look at this similarity. But the actual work, the core representational job, is done by the model itself and the specific similarity we've identified. Language is the pointer, the signpost, but the destination and the path are extra-linguistic. This is why so much cutting-edge science feels deeply mathematical, deeply model-based, and perhaps less reliant on plain English than we might initially assume. So does this mean math is more important than language in science? Or vice versa? Let's resist that urge to rank them. It's a false choice. Language is useless without the perceptual tools, the abstract models, the graphs, the instruments that give it meaning and application. Think about it. Could we even formulate a scientific hypothesis without concepts derived from observation or modeling? Conversely, imagine having all these amazing perceptual and abstract tools, but no language to combine them, structure them, communicate them, build upon them recursively. Our representational power would be incredibly limited. It's like having a super powerful engine but no gearbox or steering wheel. They are fundamentally intertwined, constituting each other's power. Okay, let's shift gears slightly. We've seen science uses lots of representations, linguistic and otherwise. But here's a crucial point. Are any of them perfectly precise and accurate? Spoiler, probably not. Before we dive deeper, we need to be careful with our terms. Precision refers to how finely defined something is. Accuracy refers to how close it is to the truth. Think about John's height. If I say he's exactly 6 feet, that's precise, but if he's actually 5 feet 11 inches, it's inaccurate. Now, if I say his height is 6 feet close enough, that's imprecise. What counts as close enough? But within that fuzziness, it's perfectly accurate. See the difference? Imprecision is about vagueness, lack of fine detail. Inaccuracy is about deviation from the true value. We'll use inexact as a catch-all for both being imprecise, inaccurate, or both. Now, it's obvious that pictures, maps, and diagrams are inexact. A map of London won't show every single crack in the pavement. But here's the kicker. Most of our linguistic representations are also inexact, even after scientific refinement. Science gives us better clocks, telescopes, microscopes, but does it eliminate inexactitude? Mostly not. The only real exception might be certain parts of pure mathematics, where ambiguity is actively avoided. Take color. Our everyday idea of red is simple, an intrinsic property, reality. Way more complex, involving light surfaces, our eyes, our brains. That naive idea is inaccurate. Same goes for space and time. Our intuitive notions get seriously challenged by relativity. Even our basic concept of objects having clear boundaries and identities turns out to be an idealization when you dig deep enough. So, inexactitude isn't just a flaw we overcome. It seems to be baked into how we represent anything. Many people think science is the great exactifier. We find the true laws, the fundamental particles, the precise definitions. But is that true? Have we ever pinned down some perfectly determinate natural kind or quantity that our scientific terms latch onto exactly? Look at mass. Newtonians thought it was simple, well-defined. Then came special relativity boom, rest mass versus relativistic mass. General relativity muddies the waters further, blurring mass and energy, making gravitational mass energy non-localizable. Quantum field theory throws in renormalization, making mass a parameter needing adjustment. At no point has mass been attached to some perfectly clear, unambiguous physical reality. It's always an idealization, a simplification. And the same goes for most of our scientific terms. Even our laws are often idealizations, describing simplified scenarios. So, the big takeaway here is that human representation, whether it's pre-scientific or scientific, linguistic or visual, is inherently inexact. It's not some logical flaw in the concept of representation itself. There's no rule saying representations must fail. Rather, it's a practical limitation. Our cognitive abilities, our tools, our languages, they're just not powerful enough to capture the sheer, potentially infinite complexity of the world with perfect fidelity. It's like trying to describe a fractal pattern with a finite sentence. You'll always lose detail somewhere. How do we judge these imperfect representations? We evaluate them based on how well they represent reality. For analog things like maps, we talk about accuracy. Is it accurate enough for navigating a city? For statements, though, we usually say they're simply true or false. There seems to be no wiggle room, no relativization to respects or degrees like with maps. This makes truth seem fundamentally different from approximate truth. Approximate truth sounds fuzzy, maybe even incoherent, if you demand absolute precision. But approximate truth makes perfect sense if you specify what it's approximately true about and to what degree. A statement is approximately true if it captures the relevant aspects of reality sufficiently well. This leads to a puzzle. We often think of truth as exact correspondence. The statement matches reality perfectly. That sounds neat, like a perfect mirror image. But remember, our statements are made of inexact words and concepts. How can something built from inexact parts have exact truth conditions? When we use a map, we judge its accuracy relative to the territory and our needs. Shouldn't statements be judged similarly? If a statement is about John's height, shouldn't we ask accurate enough for what purpose? The argument here is that we do implicitly relativize truth evaluation, even if we don't always say it. And the standards themselves, they depend on our interests, which are never perfectly fixed. So the conclusion drawn is quite radical. Statements might not have exact truth conditions. Truth itself might be inherently approximate, context-dependent. So, if truth isn't perfectly exact, how do we make sense of it? Philosophers have tried various accounts of vagueness, but many stumble. Take supervaluationism. A vague statement is true if all its possible sharpenings are true. Sounds good, but what counts as an appropriate sharpening? That term is just as vague. Epistemicism offers a different route. Everything is precise, but we just don't know the exact boundaries. Think of the classic Sorites paradox, removing grains of sand one by one. Epistemicists say there must be a precise point where it stops being a heap, we just don't know where. But we can counter this by adding humanly accessible to the claim of precision. More importantly, epistemicism struggles with the deeper issue. If vagueness is just ignorance, how do we explain the fundamental inexactitude of all our representational tools? Not just our knowledge of vague terms. It feels like there's something more going on. We need a better way to understand truth evaluation when everything is inherently fuzzy. The author suggests looking back at how we evaluate analog representations. Remember the map. Its success depends on similarity to the territory in relevant ways. Could we apply this idea to statements? Maybe truth, even for seemingly precise statements, involves a kind of similarity to an underlying idealized or precise version of what the statement is trying to capture. Think of it like this. The map is an approximation, but it's evaluated against the territory. Perhaps a statement is true if it's sufficiently similar to some idealized precise proposition that accurately describes reality within the context of application. Let's revisit John's height. If I say John's height is 6 feet precisely, this is likely false because nobody has such an exact height. Yet, in everyday situations, we often treat it as true. Why? Because the tiny discrepancy doesn't matter for whatever we're doing. We call this situation the conditions of application obtaining. This precise statement is inexact because it's inaccurate. Now consider John's height is 6 feet close enough. This is imprecise, but if it falls within the accepted range for the current conditions of application, it's literally true. It achieves truth by virtue of its imprecision covering the relevant variation. Notice the trade-off. Precision leads to potential inaccuracy, while imprecision allows for accuracy within its bounds. But wait, doesn't saying John's height is between sand and 9 feet solve the problem? Surely that's true. Well, maybe not. Think about it. Heights fluctuate. Even if we fix a moment, what counts as height, posture, include hair, skin, relativistic effects, quantum uncertainty. The problem isn't just the number 6 feet, it's the concept of height itself. Any attempt to operationalize height precisely, define exactly how to measure it, will result in a new definition that's now accurate but incredibly imprecise, open-ended. So, the interval statement, sand to 9 feet, still suffers from the same fundamental issues as the single-value statement. It's precise in specifying the interval, but the underlying notion of height remains idealized and inaccurate. Many seemingly true statements about the world might face similar challenges. So, we have this interesting dynamic. Imprecise statements often work well because they're accurate enough for their purpose, while the corresponding precise, idealized statements are often inaccurate but allow for truth evaluation. Think of them as semantic alter egos. To understand the force of the imprecise statement, John is tall, we mentally refer to its precise counterpart, maybe John's height is 6 feet by inches precisely. We then evaluate that idealized statement for truth, considering if it captures the relevant aspect of tallness in the given context. If the precise idealization is true enough, literally true, given the context, then the original imprecise statement functions as true. Truth here is achieved by smoothing over inaccuracy with imprecision, always relative to the current concerns. This brings us to semantic contextualism. We often ignore the fuzziness of our representations because it doesn't bite us. Think about knowledge. Epistemologists talk about contextualism. What counts as knowing something can change depending on the situation. High-stakes situations demand higher standards of evidence. Similarly, the author proposes semantic contextualism. The standards for what counts as a true statement might also shift depending on the context. We operate on platforms of presumed exact truths, background assumptions we take for granted to get started. But these platforms aren't perfectly solid ground, they're provisional. When problems arise, we need to refine our representations, tighten our standards, just like we might need more evidence for knowledge claims. It's a spirit of defeasibility, ready to revise when challenged. Why did people get tempted by epistemicism, the idea that there's one ultimate precise standard of truth? Perhaps because they conflated the idea that every context needs a suitable platform with the belief that there exists one universal platform that could handle any situation if only we knew it. But the author argues that such a universal human-accessible platform is likely impossible. It's probably beyond our reach. So, we need a practical system for evaluating representations that doesn't rely on some hypothetical ultimate precision. We need to work with the inexactitude we actually have, adapting our standards based on the context and the problems we face. Let's bring Huxley's applied common sense back in, but this time to think about how scientific representations evolve. It's a process, a rational reconstruction of history. We start with our rough everyday tools for representing the world. We use them to solve problems, but in doing so, we inevitably encounter limitations. This pushes us to correct, extend, and refine our representational methods. These improvements become part of our new toolkit, and the cycle repeats. We constantly strive for better accuracy and greater precision. Now, can this process ever truly end? Can we reach a state of perfect, exact understanding? Maybe in theory. Peirce talked about a long-run limit of inquiry. But as Keynes famously quipped, in the long run, we are all dead. Practically speaking, the quest for perfect representation seems endless. Alright, shifting focus now to scientific discovery. Here we hit a fascinating paradox. On one hand, there are strong arguments from philosophy, history, and sociology, suggesting that there's no reliable logic of discovery, no universal scientific method that guarantees finding new truths. Think about the problems with induction, the role of luck, the social dynamics. Yet on the other hand, the giants of early modern science, Bacon, Descartes, Newton were obsessed with finding such methods. They felt that past discovery was hit or miss, driven by genius or fortune, and they wanted a systematic, guaranteed way to produce new knowledge. Their goal was to level the playing field, to make science less dependent on individual brilliance and more on a shared rational procedure. Initially, the idea was generativism. The path you take to reach a conclusion is crucial for its justification. Finding a reliable method was key. Think deductive proof, but things shifted. As science moved into deeper theoretical territory, gathering enough data for solid induction became impossible. Enter the method of hypothesis. You propose a theory, test its predictions, and refine it. This became dominant. This led to consequentialism. The way you come up with a hypothesis doesn't matter as much as how you test it. The tests check if the hypothesis logically entails observable consequences. Tested, not proved, because confirming the consequence doesn't guarantee the hypothesis is true, affirming the consequent fallacy. Science became seen as a cycle of conjecture and refutation, never reaching certainty, always improving. There was a real methodological inversion. Hypothesis testing became the official method, while induction was relegated to historical studies. This consequentialist view got formalized by the logical empiricists and Popperians. Hence Rachenbach's famous distinction between the context of justification, how we justify beliefs, and the context of discovery, how beliefs arise, became a cornerstone. Philosophy focused on the former, historians and psychologists on the latter. Popper emphasizing theories as free creations seemed to close the door on discovery as an epistemological topic. However, around the 1960s, interest revived. Peirce had pointed out earlier that discovery can't be entirely detached from justification. You need some chance that your hypotheses might be fruitful. Efficient search requires more than just random guessing. Interestingly, Reichenbach himself didn't fully commit to strict consequentialism. He kept induction as a self-correcting, long-term method, and even explored causal networks. The pendulum started swinging back. So why the pessimism about finding a magic bullet for discovery? First, the founders themselves couldn't agree. Second, their own methods were discovered by luck, hardly a model of reliability. Third, the initial claims were ridiculously strong, one universal method for all content. How could that possibly contain all future discoveries? And there's little evidence it explains modern science's success. Specific methods tailored to domains often work better. No free-lunch theorems back this up mathematically. Fourth, creativity involves imagination, not just logic. Fifth, philosophical attacks on realism undermine the very goal of discovering truth. 6. History and sociology showed discovery is messy, socially constructed, hard to attribute cleanly. Kuhn showed it's complex. Sociologists showed it's social. 7th. AI's early promise as a discovery engine fizzled out. Programs were often too simplistic, working on clean problems, not the messy reality of frontier research. Expert systems helped with routine tasks, but weren't revolutionary. But hold on, there's optimism too. Despite the setbacks, science today uses incredible tools: gene sequencers, complex computer models, sophisticated statistical packages. We're not building Hao Jiuqian yet, but we have powerful aids. The tradition of data analysis from mill to modern statistics has given us ways to distill knowledge from ignorance. History and sociology, instead of killing discovery talk, have nuanced it. Discovery isn't a simple flash of insight, but a complex process involving communities, social negotiation, and contingent events. We can use discovery neutrally to mean innovation or problem solving. Kuhn showed discovery isn't always linear. Small steps can lead to big leaps, and logically, we're broadening the concept of logic beyond strict deduction. Hintika's interrogative logic work on abduction, adaptive logics. These explore reasoning strategies. Even finding a deductive proof can be a discovery. Leonard called discovery ubiquitous. Maybe we're rediscovering the importance of discovery, but in a more realistic, nuanced way. Is AI completely dead as a path to discovery? Not necessarily. Two areas are particularly exciting. Case-based reasoning basically implements Kuhn's idea that we solve new problems by adapting solutions to old ones. You build a library of past cases and try to find similar ones for new problems. This explicitly uses similarity, analogy, metaphor, things traditionally sidelined in formal logic. It acknowledges the creative power of relating the new to the known. Then there's model-based reasoning. This involves using dynamic models, simulations, to explore possibilities, test ideas, and even discover new concepts. It tries to capture aspects of human intuition, visualization, and tacit expertise, exploring how different forms of representation can enhance our thinking. These approaches seem closer to capturing the messy creative aspects of scientific work. Two recent hot topics in discovery logic are evolutionary computation and Bayesian causal networks. Evolutionary computation sounds wild. Instead of solving problems step by step, we let candidate solutions evolve. Like natural selection, but for algorithms. You start with a population of potential solutions, test them, keep the good ones, mix them up, add random changes, repeat. It's surprisingly effective. Some argue all creativity works this way: blind variation plus selective retention. If universal Darwinism holds, maybe we have a general discovery method after all. It's ironic. The old method of hypothesis is like a trickle of BVSR. Evolution scales it up massively. Then there's Bayesian causal networks. This uses stats and computation to infer causal relationships from data, even if the data is incomplete or observational. By analyzing correlations and independencies, it can suggest plausible causal structures. This is huge. It potentially allows us to discover causality without controlled experiments, pushing correlational methods much deeper into causal territory and giving realism a boost. So, where does this leave us? The big conclusion is that the neat global split between context of discovery and context of justification is probably wrong. There was never real agreement on such a clean division. Science is messy. Discovery-like activities are everywhere, from formulating a research question to writing a grant proposal, even to deciding which philosophical theory is best. By treating discovery as external to philosophy, philosophers cut themselves off from understanding how science actually progresses, how knowledge grows at the frontier. They lost touch with the how possibly problem. How do we make progress when we don't know where we're going? Ceding discovery to others threw out valuable insights along with the flawed theories. For those interested in digging deeper into these complex and fascinating topics, the provided reading list offers a wealth of resources. From foundational texts by Teller and Nichols to detailed explorations of models, vagueness, the history of discovery debates, and cutting-edge computational approaches, there's plenty to explore.